my channel, and today I'm going to be talking about the binomial theorem and cylindrical coordinates. So let's begin by talking about the binomial theorem. So what is the binomial theorem itself? Well, the binomial theorem is a theorem that lets us compute a plus b raised to the power of n, as listed over here. Or in other words, it lets us take a binomial and multiply it by itself n times. And it lets us do that more efficiently than using standard algebraic methods. So that's essentially what the binomial theorem actually is. So this over here is the binomial theorem. Now you may be wondering, what is this formula over here? Now let's just say we want to compute x plus 2 raised to the power of 7. Now we can use the binomial theorem to do this because it's much more quicker and more comprehensible to understand, because when we're doing it the old-fashioned way, it just takes a long time and it's just more tedious. Okay, so let's just say we want to find the fifth term of this essential expression. So once we just compute this, we will just have a big expression, and we want to find the fifth term of that expression. Then instead of just using the binomial theorem or any standard algebraic method to just essentially search for the fifth method once we've done computing it, we can just directly go to this formula and then go to the specifications and just plug it in, and therefore we can get the value in the fifth term's place. Okay. Now you may be wondering, so if we have the binomial theorem over here and this formula over here, what branch of mathematics are they in? Well, the branch of mathematics they are in is algebra. Now you may be wondering, why aren't they taught in an algebra class? The reason is because the binomial theorem is a type of algebra that should be taught in algebraic class, but involves another step of algebra. So if you were thinking about this, say we take a quadratic equation. In order to solve that quadratic equation, we can use the quadratic formula. We can factor the quadratic, and we can do multiple more methods to essentially reduce that quadratic into something simpler that we can compute very easily. Now, this binomial theorem is like that formula, except a formula is just a definite thing. You don't have arbitrary variables. Well, we do have arbitrary variables in the quadratic formula, but we don't have a length that's near infinity. So as you can see over here, we can write the binomial theorem as if it's going to infinity. We can keep on continuing. And this is kind of special to the binomial theorem. In a formula, you can't really do that. In the quadratic formula, namely, the quadratic formula just has, for example, one definite formula. There's no extra add-ons or nothing you can subtract off of. It's just a one definite thing. Over here, we can continue forever. And it's kind of like a pattern too. Plus, the binomial theorem takes different types of mathematics and combines them. So in an algebra class, you probably might talk about factorials a little bit. But in the binomial theorem, you use pretty much multiplication, addition, and pretty much all the things you learn in algebra, but then use factorials into it too. So you're trying to essentially incorporate other branches or other types of mathematics into this. Whereas in a regular algebraic formula or in regular algebra class, you won't talk about these extra things. Okay, so now let's actually start by doing an example problem. So let's say we have x plus 2 raised to the power of 4. Now let's not do this manually. Instead, let's do this the smart way. By manually, I mean by using standard algebraic methods. By essentially doing a quicker method, I mean using the binomial theorem. Okay, so the binomial theorem says that we have to take an a, b, and n. So we have to define three variables here. Now this is pretty easy. We'll define our a to be x, b to be 2, and n to be 4. Okay, so we've got our variable checklist. We'll write VC. So we got our variable checklist done. Now let's essentially start going through this formula. So we have a raised to the power of n. So a is going to be x. This is x raised to the power of 4. So the first term is going to be x raised to the power of 4. Okay, so we have x raised to the power of 4 as our first term. Now let's look at the next term in the sequence. Na to the n minus 1 times b. So we have n, which is 4, times a to the n minus 1 x to the x cubed times b times 2. So let's just do the third term, then we'll talk a little bit more about what we have so far. Now we had n, which is going to be 4, times 4 minus 1, which is 3, all over 2 factorial, which is 2, a to the n minus 2, that's x squared, and that's going to be b squared. Okay. So essentially, as you can see over here, we've got this essential expression over here. So this is going to be our essential expression. What I mean by that is this is going to be the thing that we're going to be observing in order to find patterns in the binomial theorem. So as you can see over here, the first thing in the binomial theorem is always going to be a raised to the power of n. That's pretty obvious because in the formula, it's a raised to the power of n. Pretty simple. So let's just talk about factorials a little bit. So a factorial is a pretty simple concept to understand. Let's say we have 5 factorial. This is just 5 times 4 times 3 times 2 times 1. Now we can exclude the 1 part because that's just the same thing. This is 20, this is 6. We have to multiply them. This is going to be 120 times 1. This is going to be 120. So we essentially just multiply the number itself and all the numbers below it till 1 consecutively. Okay. That's essentially what a factorial is. Now, we use factorials here a lot. 2 factorial is obviously 2 because 2 times 1 is therefore 2. Now, the second thing that we notice is that excluding the first term, the powers of b keep increasing. So we have b squared, and so on and so forth. Now, you may conjecture a hypothesis that actually might exist. So you may conjure a hypothesis that might exist. So what I mean by that is that what if this ends till we have b to the n? And this is actually true. The formula stops when we have the formula stops when the previous term is going to be just excluding x, then the next term is always just going to be b to the n. So in the previous term has a power of x raised to the power of 1, right, blah, blah, blah. The next term is always going to be b raised to the power of n. So that's essentially a pattern in the formula. So the previous term just has an x variable, an x with no power. Then the next term is always going to be b raised to the power of n, and then the formula is terminated, or the formula stops. So essentially, that's where the formula stops. So let's just simplify this so far. So we have x raised to the power of 4 plus 4 times 2 is 8, 8x cubed, plus 4 times 3 is 12, 12 divided by 2 is 6, 6 times b, now we have to plug in b is just 2, so that's 2 squared, so 2 times 2 is 4, so we have 12 times 2 is 6, 6 times 4 is 24, 24x squared. Now let's continue. Now since we're continuing, we'll change this to an arrow mark. Okay, so we have n, which is just going to be essentially 4 times 3 times 2, 4 times 3 times 2, all over 3 factorial. Well, what is 3 factorial? 3 factorial is just 3 times 2 times 1, or 6. Then a to the n minus 3, well, that's just going to be x, and b cubed is going to be 8. So simplifying this is just going to be x to the 4 plus 8x cubed plus 24x squared plus 12 times 2 is 24, 24 to 6 is 4, 4 times 8 is 32, 32x. Now, you actually see the pattern right now. We just have an x with no power. Well, it is power, it has 1, but like when you're writing it, you really don't write 1, so you just write an x. So you can see it has no power written on top of it, even though it's imaginary 1. It doesn't have anything other than 1, so therefore the next term must be b raised to the power of n. Well, what's b raised to the power of n? That's 2 raised to the power of 4, and that's going to be 6 cubed. So essentially, this is going to be our final form. We can draw an arrow right now. Okay, so the simplified form of x plus 2 raised to the power 4 is x raised to the power 4 plus 8x raised to the power of 3 plus 24x squared is 32x plus 16. Okay. And also notice one pattern. We go n times n minus 1 times n minus 2. And we keep going pretty much all the way. So we got 4 minus 1, 4 minus 2. We keep going all the way until we find the pattern where we have, in the previous term, we have just an x variable with no arbitrary power other than 1. And therefore, we're going to have the next term is just b raised to the power of n. So that's a specific pattern we see over here. And once you get used to the binomial theorem, you don't even have to recall the formula itself. It'll just come automatically, like the quadratic formula. When you take the quadratic formula to apply to quadratic, you don't have to reference it or first write it down or think about it in your brain. You just plug in the numbers as naturally as you go. Same with the binomial theorem. Once you essentially get the hang of it, you can just do it continuously and really fast. That's what makes it quick and efficient. On the other hand, if you use standard algebraic methods, there isn't really a formula. So every time you have to do it manually. Even if you get really fast doing it manually, sometimes you will get stuck because you have to memorize it. There isn't a specific type of guaranteed formula that you have. It's just manual things. Okay, the reason we have this left is because we're going to be using this formula. Let's say, so this has 1, 2, 3, 4, 5 terms in it. Now let's say we want to find the fourth term. So let's say find the fourth term of x plus 2 raised to the power 4. Okay, so let's just say this is our problem over here. Now what do? Instead of just doing the whole binomial theorem and then just calculating and then just counting them to find the fourth term, we can just use this simple formula. To check, we'll just do 1, 2, 3, 4, 5. So this one right over here. Okay. So the first thing we're going to do is we're going to define r plus 1. So we're going to set r plus 1 equal to 4. That means r is equal to 3. Now what are we doing it? Notice the formula says this formula for r plus 1 term, or for the r plus 1 term. The reason for writing this is because r plus 1 is essentially just going to be the parent term, or what I mean is r plus 1 is going to be the main term which we're going to be trying to calculate for. That's essentially what r plus 1 actually is. Now, so we've essentially gotten r now. R is just going to be 3. Since r is just going to be 3, you can now start applying it to this formula over here. Now, let's just check our coefficients really quick. The first one is x to the 4. Second one is 4 times 3, or 12. 12 over 2 is 6. 6 times, well, the second term actually is just going to be 4 times 2 is 8, and then 12 over 2 is 6. 6 times 4 is 24, and then 4 times 3 times 2 is just going to be 24 over 6. That's just going to be 4. 4 times 8 is 32, and then 2 raised to the power of 16. And it's important that whenever we're doing the binomial theorem, we have to check our coefficients, because your coefficients is what makes a binomial theorem special. Normally, when you're doing it manually, you don't get the essential coefficients automatically. You just have to keep on multiplying, keep on doing things. You just have to do it very tediously. However, the binomial theorem nearly gives us the coefficients. Okay, so continuing with this problem over here. So we have r plus 1 is equal to 4. Therefore, r is equal to 3. So n is going to equal to 4 in our variable checklist. Now, let's just first do this. But we have to define what our n minus r plus 1 term is. We have to stop at the n minus r plus 1 term. Well, n is just going to equal to 4. 4 minus 3 plus 1. That's going to equal to 2. So we're going to stop at 2 right now. So 4 times 3 times 2. We have 4 times 3 times 2. How do we get this? Well, n is 4. 4 minus 1 is 3. 4 minus 2 is 2. 4 minus 3 is just going to, we're going to stop at 4 minus 3 plus 1. That's 4 minus 2, which is 2. So we stop right there. Now, what is r factorial? R is 3. 3 times 2 times 1 is equal to 6, which is equal to 3 factorial. So essentially, 6 is going to be our denominator. Now, let's first compute this. 4 times 3 is 12, 12 times 2 is 24, 24 over 6 is going to equal to 4. Now, a to the n minus r, n is 4, r is 3, 4 minus 3 is just going to be 1. So we have 4 times x, and right now it's starting to look like the fourth term, and as an x variable with no power other than 1 on top of it. Then we have b to the r. Well, what's b to the r? That's 2 raised to the power of 3. 2 times 2 is 4, times 2 is 8. So we have to multiply it by 8, and in turn we get 32x. So as you can see over here, we got the value on the fourth term really quickly, but just using this simple formula. Okay, that's essentially the binomial theorem. Once you get the hang of the binomial theorem, pretty much it's going to be very easy to compute anything, any expression of the form a plus b raised to the power of n. Okay, so now that we've talked about that, let's move on to cylindrical coordinates. Now, what are cylindrical coordinates exactly? Well, right now we're using the rectangular coordinate system, or the 3D rectangular coordinate system to be precise. If we want to define anything in space, you'll notice we're excluding the principles of physics. We're thinking in pure mathematics. In physics, we're living in a 4-dimensional space, therefore we have to include a variable of time. But right now, we're just thinking of 3-dimensional space. To define an aeroplane in the sky, what do we use? Longitude, latitude, and altitude. That's just x, y, and z correspondingly. Now, maybe not the exact terms in what I said in the specific order, but essentially we just have x, y, z defines any point in 3D space. And we're going to call that the rectangular 3-dimensional coordinate system. So we can even draw that to represent it. So let's just say we pick a point over here. This has to have x, y, z. Now, I created a video on something called polar coordinates. Polar coordinates is another type of coordinate system. Now, in the rectangular or Cartesian coordinate system, we just have x, y, and this is 2-dimensional. Now, in the polar coordinate system, we have r, theta. Theta refers to an angle, and r refers to the length of the line. So essentially, we just have different things over here. But each of these represent the same point. So we can represent a point in 3-dimensional or in 2-dimensional space over here with different things. Namely, we can use Cartesian coordinates or polar coordinates. Namely, same in a 3-dimensional coordinate system, we can also use different coordinate systems to refer to the exact same point. So the rectangular coordinate system is what we use the best. We use it in most things in classical mechanics and physics, biology probably, chemistry probably, and even in the real world and engineering. However, sometimes in engineering and even physics, we use the cylindrical coordinates. As the name suggests, cylindrical coordinates essentially imagines a cylinder. So we're referring and referencing everything to a cylinder. Now we're not going to be talking about the geometrical perspective today, but rather we're going to be talking about the algebraic perspective. Now notice that in the rectangular coordinate system when we need x, y, z, we have different parameters for the cylindrical coordinate system because we're referring it to a different type of 3-dimensional object. Okay, so it's very important that we must understand that we have some conversion formulas, and we have a specific type of problem we're going to be today. So let's look at all the conversion formulas. So we have x is equal to p times cosine of theta, y is equal to p times sine of theta, and z is the same. I'll talk about what that means later. Tangent of theta is equal to y over x. Tangent or arctangent of y over x is equal to theta. P is equal to square root of x squared plus y squared, and p squared is equal to x squared plus y squared. So p is equal to the square root of x squared plus y squared, and p squared is equal to x squared plus y squared. Now we have to talk about the main difference. So in the rectangular coordinate system, we have x, y, z, as I mentioned. In 3-dimensional rectangular coordinate system, cylindrical coordinates, we have p, theta, z. Now you may be wondering, are the z's the same? And yes, indeed. The z's are the same. So when we're trying to convert between cylindrical coordinates and rectangular coordinates and vice versa, we don't have to do anything to z. We just have to look at the x's and y's. That's the main important thing. So we have P, theta, and Z. So that's our main goal. Okay, so when we're taking, so let's just say we know what theta is, and we know what P is. Now Z is the same, so, and they give us Z. So if we get from P, theta, and Z, we know this, we can easily go to X, comma Y, comma Z. How? Well, Z's are the same, obviously. And in order to transfer these, we can just use C's formula. X is equal to P cosine of theta, and Y is equal to P sine of theta, given this. Now, on the other hand, if you want to go from vice versa, we want to go from X, comma Y, comma Z, or the rectangular three-dimensional coordinate system, to cylindrical coordinates, we can use another set of formulas. What can we use? Well, we can use this. We can also use this. Now, using these two formulas, we can essentially just convert between cylindrical coordinates and rectangular coordinates itself. Notice we will talk about the geometrical perspective of this in later videos, but right now we're going towards the algebraic perspective. Okay, cylindrical coordinates over here. So we're going to be dealing with the problem. So we have 3, 6, and 9. Now, obviously, this is going to be the rectangular three-dimensional coordinate system. And we want to go all the way to the rectangular coordinate system. That's our main ambition in this purpose. Okay. Now, how do we do that? Well, obviously, we can use some of the formulas over here. Now, what formulas can we use? Well, obviously, let's write our answer over here. We already know 1/3 of our answer. What do we know? Well, we know, obviously, that the z's are the same. So we'll just have 9. Now, we have to just operate on these using the formulas to get the P and the theta. So let's first get the P first. So P is just equal to the square root of x squared plus y squared. Now we can plug this in. So P is equal to 3 squared plus 6 squared. This is 9 plus 36 is equal to P. And the square root of 9 plus 36 is equal to P. And this is equal to the square root of 45. Now we can simplify this to 9 times 5 is 45. So we can do 3 square root of 5. Like this. So as you can see over here, we can simplify this to 3 squared root of 5. So this is going to be our P over here. Now I've written this in a decimal sense over here. 6.70820 and something like that, all the way continuously. Now we kind of essentially got our P, so we'll just write 6.7 over here. So we've got our P, now theta. Now there's a smart trick for theta. So we know that the tangent of theta is equal to y over x. Using this essential formula, we can deduce that the arctangent, which is just the same as the tangent of 1 of y over x, is equal to theta. Is equal to theta. So what is the arctangent of y over x? Well, y over x, 6 over 3 is just going to be 2. So the arctangent of 2 must equal to, well, over here, 63.4 degrees. This is what the arctangent is equal to. 63.4 degrees. Okay, so we can write 63.4 degrees over here, and therefore, we've essentially just gotten our answer. Okay, so we've successfully transferred from rectangular three-dimensional coordinate system all the way to the cylindrical coordinate system. Now let's transfer to the back. So obviously we got 1/3 of our answer because the z's are the same. Now let's go look at the essential. Let's go try to find x's and y's. So let's first find the x value. X is equal to p cosine of theta. Now p is just going to be 6.7. We won't write all of it because there's more. 6.7 times cosine of theta. The cosine of theta is 0.44775. And once we just do those operations, we'll get something to about 3, which is our original x value. Now, if we do y times p cosine of theta, well, p is just going to be 6.7 as we're shortening it, and the sine of theta is going to be 0.894154. Now you may be wondering, well, what is the sine of theta and cosine of theta? Well, the theta is 63.4 degrees. Taking the sine of that, we'll get that, and taking the cosine of that, we'll get that value. Okay, so now that we've essentially got that, once we multiply these, we'll just get y is about 6. Now, if we took all the exact values, it would be y is definitely equal to 6 and x is definitely equal to 3. But right now, we can't do that. So this is essentially how we convert from there to there. Now, you might be wondering, well, why in the first place do we have the binomial theorem, a purely algebraic theorem, and cylindrical coordinates, which, by the way, is taught in pre-calculus or at maximum a trigonometry class? Why are these two subjects being correlated? Well, notice I didn't talk about the geometrical perspective right now. The binomial theorem is something that should be taught in algebra, and it's purely algebraic. Cylindrical coordinates might be in a different level mathematics, but it revolves heavily on algebra and trigonometry. So using both of these algebraic and trigonometric techniques, we can get a better understanding of our world, even though they just use mostly the same algebra, multiplying, addition, subtraction, blah, blah, blah. Other than the cosine of theta and sine of theta, these are pretty much a basic algebra student can understand. Okay, now that we've talked about that, we can make this video to an end. If you like this video, if you like this channel, please subscribe to learn more. Thank you.